So we get started. We're going to do more advanced caching today, and we're going to go fast and end early, hopefully. Okay, I fixed this so you have your homework due April 3rd. Go with the website again, and you know this. So we're going fast. We're just going to skip through slides. So today we'll do more and more advanced caching. So hopefully this, as I told you earlier, it's an exciting topic. And a lot of the topics that we'll cover today are applicable outside the context of computer architecture also. Whenever you have caching, you can imagine lots of these concepts to be applicable there. For example, in distributed systems, whenever you do some caching, you'd like to utilize your cache efficiently, or your web cache, right, in your browser, in software. You'd like to utilize it much better. A lot of the concepts that we'll talk about will be applicable. But just a review, this is a particular structure of the hardware cache, right? You don't see a lot of direct map caches in software. Why? Because associative caches are easier to implement in software, right? You can more easily search the structures. But we've started with this direct map cache where you have this tag store and the data store, and where a block in memory can map to only one location in the cache, basically one tag and data entry in the cache. And that's determined by the index, right? And many blocks share the same index, which means that those blocks map to the same set, right? And that's why you get conflict misses. This was the direct map cache. Why do you want a direct map cache? Because it's simple, right? You just have one tag comparator. You access the tag store with your index, get the val bit and the tag, compare the tag to the tag bits in the address, and if it matches, that means that the data store stores the block that corresponds to this address that you're looking for in the cache. And this is simple. And you normally don't see this kind of structure in software caches, but you see it in hardware caches because it's simple to implement, right? Now, the problem with this is you have conflict misses. You have many blocks mapping to the same index in your cache. So we've seen one solution to that, which is basically increasing the associativity. Enable a block to map to multiple possible locations in the cache by making your sets, giving your sets the ability to host multiple blocks, right? Basically, you can have multiple blocks in a given index in the cache. That's the idea of set associativity. And this is a two-way associative cache, right? Now, in your set, you can host two blocks. What is a set? A set contains the blocks that have the same index in your cache. OK. So now you increase add more complexity as you increase the set associativity. The upside is you hopefully get better hit rate. You can accommodate conflicts better. But also there's slower access. It's not only complexity, but hit latency increases, and your tag store size increases. And we've seen that you could go to full associativity, which is now any block in memory can map to any location in the cache, right? A block in memory can map to any location. Now the search, this is essentially a content addressable memory, where the content is your address. Okay, and this is the most complex. So we will later look at how to approximate the benefits of associative caches without adding more associativity into the cache. Or, yeah, exactly, without having more associative, without having this parallel search. And you can imagine some methods for that, but let's hold on for that. Last time we've talked about approximations of LRU. Whenever you have full associativity, or whenever you have associativity, now when you try to put a new block into the same set, and if the set is full, which means that if the set already hosts multiple other blocks, you need to replace something. Replacement policy determines your performance in a set associative cache. That's not a problem in a direct map cache, right? You have only one block to replace. Although you have another problem over there, right? Another possibility. Do you actually replace the block that's already in the direct map cache, or do you put in the new block? Right. That's a choice. Normally, many caches replace the block that's already there and put the incoming block into the cache. But you actually have a choice, right? Do you actually put the incoming block or not put the incoming block into the cache? You can filter out the incoming block, not cache it. If you have a predictor that says, oh, this block is not going to be reused later on. And we may get into those mechanisms, and people have developed mechanisms to predict the reuse of blocks and decide whether or not to insert a block into the cache. But let's assume that you do insert the block. If you insert the block, what block do you replace? That's the replacement. So there are two key decisions: insertion policy and replacement policy. Insertion policy will not cover as much. I guess insertion policy, do you insert the block, incoming block into the cache? And the answer could be yes or no, right? And once you decide to insert, where do you insert? At what priority do you insert? This determines when the block will be replaced. I guess I'll call this at which priority level. You can think of replacement as a prioritization mechanism, right? You have some priorities with the blocks, and you, whenever you need to evict one block, you kick out the one that has the least priority. Right? And when you insert the block, you can put it at some priority level. Actually, there's another policy in a cache, which is the promotion policy. And this is basically what happens on a hit. On a cache hit, how do you change the priority of the block? Priority of the block that you hit. If you're using the LRU policy, least recently used replacement, remember that you need an ordering. What is least recently used? What is most recently used? When you get a cache hit to any block, that becomes the most recently used, right? That's promoted to become the most recently used. That's the policy, promotion policy for the LRU mechanism. And everything else shifts, right? Does that make sense? Yeah. And the last thing is replacement policy. And here, when you get a miss, on a cache miss, what do you replace to accommodate the incoming block? On a cache miss, and if you decide to insert the block, what block do you replace from the cache? So all policies that govern a cache need to specify insertion, promotion, and replacement. If we look at LRU, the commonly used LRU policy says, do you insert the incoming block into the cache? The answer is yes. Promotion policy on a cache hit, what happens? How do you change the priority of the block as well as other blocks? Also other blocks, right? The LRU policy basically, if you get a cache hit on that block, you promote it to become the MRU. And every block shifts somehow, right? For example, one block that was MRU becomes MRU minus 1. And replacement policy on a cache miss, what block do you replace from the cache? LRU policy says replace the least recently used block. Right? Now, if you can define a random policy, random replacement policy, that can decide to insert or not insert. That can randomly decide this question. Right? Do you insert the incoming block into the cache? I don't know. Flip a coin and decide based on that. Right? That may not be a bad policy in some cases, especially if your cache is thrashing. Right? We'll see that. If your working set is larger than your cache, LRU will not help you that much because you're already thrashing your cache. But if you do a random policy, randomly pick what you insert in the cache, you'll keep some of your working set in the cache. And that enables you to get a better hit rate. We'll see this in a little bit more detail. You could have everything random here, right? And usually random works when you're thrashing your cache. Okay. So you could be more intelligent also. As I said, do you insert the incoming block into the cache? Then you can consult a reuse predictor. And I will not go into detail in this one, but basically what you can do is you can have a predictor that says, should I cache this address or not? It may be that, let's say you have your memory. Think about your memory. And some regions of your memory may have better caching behavior, right? You may have better locality in some regions of your memory. Why? Because they may host data structures that you have good locality on, right? That you operate that way. And some other regions, for example, the stack, may have good locality because you keep operating on it a lot. Some other regions may not have good locality. And some other regions may depend on what data structures are hosted on that. So you might design a hardware predictor that basically takes the address. This is the address that you're looking up in the cache. In this indexes a predictor. Let's call this reuse predictor. That basically has a bit saying cache it or not cache it. Right? And you can train that based on the behavior that you've seen based on this address. Of course, you don't have that particular address, but you have a coarser grain, right, region. So you take, for example, you take the page number and index this table that says, oh, this page has good locality, maybe. Right? People have proposed this kind of predictors. And there's some predictors that are used in existing processors that don't exactly operate this way, but they try to minimize, they try to be more intelligent. Does this make sense? I'm glossing over the implementation details, but you can imagine how this works, right? You divide memory into coarser grain regions, and you check whether that coarse grain region has good locality or bad locality. And this works because you can do many accesses to that coarse grain region. Let's say this coarse grain region is of size 1 megabyte, which means that you chop off the 10 bits from the address and use this part of the address to index into this predictor that tells you cache or not cache, a block that belongs to that region. You can imagine many different policies to update this. These could be 2-bit counters, right? Very similar to the branch predictors that we've seen. You may see a block here that has good locality. And how do you figure out that has good locality? If you get a hit on that block, you decide to cache it. And if you get a hit on that block, you increment this counter. Right? And if you keep getting hits on the blocks that you've cached in this region, you keep incrementing this counter, and this counter saturates, saying that you should cache any other block that you see within this region. In some other region, it may be that you cache the block, and you don't get a hit. So you decay these counters such that they indicate not cache. Right? And you cache another block, and you don't get a hit for a while until its eviction. Then you decay the counter again, decrement the counter. And the counter eventually says not cache. And when you get to that block, get another miss in that region again, you check this counter, it says not cache, then you don't cache. That way you can distinguish what parts of your memory has good locality versus bad locality. And people have proposed many other ways of doing this. You could do this based on the load instruction that actually brought that actually is requesting this address, right? This predictor that I told you does it based on the address, but you could also have a predictor that says this load instruction itself, based on the program counter of the load instruction that requested this address to be brought into the cache, I'm going to check if this load actually brought in data into the cache that's reused later. And this could make sense also. Some load instructions may have good locality, right? If you actually are doing array accesses, for example, and you keep going back to the array, and you get good locality, you keep getting hits because of the loads that you're doing to an array, now you can distinguish what has good locality and what has bad locality based on the program counter of the load that brings it in. And some other load instructions may be accessing totally random locations, right? Imagine, for example, a load instruction that loads that loads locations from a linked list. And the linked list is allocated randomly. The addresses. So you have these nodes, and the addresses of the nodes have no relationship to each other, and you have not very good locality here. And you have a load instruction that basically loads consecutive nodes. And you may, what may happen is when you bring in some of the nodes, you will see that you don't have good locality. And if you have a predictor like this, the next time you see this load, you check this predictor. The predictor says, don't cache the block that's requested by this load. Then the hardware will not cache it. That way you can eliminate useless caching decisions. Now you can imagine that the programmer can do this also, right? If the programmer actually knows what loads have good locality in the data they bring and what loads have bad locality in the data they bring, they can mark these loads as good locality loads, and they can mark this load, for example, an array access load. If you're accessing an array with a load, it has good spatial locality, right? You might want to cache it. Whereas this kind of load, it has not good spatial locality and maybe not good temporal locality that you figure out. That way you can mark this as bad locality load. And the hardware will take this information and not cache these bad locality loads, right? It's a hint provided by the programmer to the hardware. And existing processors have this kind of hints. These are called, well, actually, these are called non-temporal loads. x86 architecture has this notion of non-temporal loads, where the load can be marked with a bit saying that this load is non-temporal. Don't cache it. Or don't cache it at one of these levels. I don't have it with me right now, but in a later lecture, we can look at the exact definition of what is a non-temporal load in an x86 architecture. But that's the purpose of this. It doesn't have good locality, so it's a hint to the microarchitecture saying that don't cache this. Don't cache the blocks that are requested by this particular load instruction. And what I described to you earlier could do this in hardware. Okay? Yes. You've been waiting for a while. I know.
So is this also used for instruction caches using branch predictors? Like, so if I have a branch, if that I predict won't be taken, I don't need to cache the instructions from that address, right?
Oh, I see. That's a good question. I don't know of anyone, any particular approach that does that. So if you actually, what you're suggesting is you have a branch instruction, and you have a hint with the branch instruction saying that I usually will not take this branch.
Or, I mean, instead of a hint, you could just use the normal branch predictor to see.
That's right, yes. You could potentially do that. You could design a mechanism. Now you're designing a mechanism for better caching for instruction caches. You could potentially do that. Right. Don't cache this because I usually don't go to this cache line, a cache block. That makes sense. That's a good idea. Maybe you can improve upon it and have a much better instruction caching mechanism. Usually instructions have very good locality, and what is done is the common approach is cache the things that you touch in the instruction space. Data space is a lot harder, actually. Okay. Anyway, we digressed a little bit, but this is important. This actually optimizing the caching at various levels is very important, and we will see some other approaches later on. Okay, we talked about last time true LRU, and true LRU was difficult to implement, right? And why is it difficult to implement? Because this replacement policy, what block to replace, is difficult to determine as you increase the associativity of your cache. And we've looked at this. So there were multiple approximations to it, not MRU, hierarchical LRU, which we covered, victim, next victim replacement, which we ended with. And I ended with this slide, which was an example of victim, next victim replacement. Do you guys remember the idea of victim, next victim? So instead of keeping the LRU order of the blocks, if you have an 8-way cache, don't keep that order, entire order. I guess in this case, we have a 4-way cache. Let's say you have A, B, C, D. Don't keep the order of what's LRU plus 1, LRU plus 2, and MRU, but instead keep the order of what is victim and what is the next victim. And for the others, you have no idea when they were reused last. And you can imagine that this scales kind of nicely, right? As you increase the associativity, you only need to keep track of two things. What is the victim? What is the next victim? And this ensures that, and when you get a cache miss on this set, the idea is to replace the victim and promote the non-victim to become the victim and pick one of the other blocks to become the next victim. That's the idea. It's very simple, powerful. This way you never evict the victim. You never evict the two things, these two things. And you can determine the victim and not next victim to be MRU and MRU minus 1 blocks. Most recently used and the next most recently used blocks, right? That way you approximate the LRU mechanism. But it's again more general, right? You could actually determine these to be anything. You could say, whatever my reuse predictor tells me as the block that's going to be reused most will not be the victim or the next victim. Right? You can keep those things here. Does that make sense? So it's really if you think of this, it's really a priority level in the cache. You're adding priority levels in the cache such that this is the eviction priority. These are the blocks that have the least priority in the eviction. Evict this one first, evict this one next, and the other one's priority is all random. Make sense? Okay, so if you look at this is one example. Well, how do you implement this? You could implement this in many different ways, right? One way of implementing it is for each block, in this case A, B, C, D, you keep 2 bits, victim, next victim. And the bit is set if this block is victim. It is not set if the block is and this other bit is set if the block is next victim. This is not the most efficient way. Depending on what your associativity is, you can have pointers to, as I discussed. You can actually have, for each set, next victim, you can have a pointer to the way. Well, I guess in this case, this points to way 0. In this case, a pointer way 1, saying that your victim is at way 0 and your next victim is at way 1. This could be more space efficient than having 2 bits per block. But this particular example shows that A is the victim, C is the next victim. I guess I was not true to my example. So this is your next victim here. And you get a hit to A. If you get a hit to A, now you're hitting on the victim. Right? If you're following something like LRU, you'd better promote this, right? So what this does is this basically makes A nothing, if you will, or other block. It's neither the victim or the next victim. And next victim, C becomes the victim now, right? And one of the other blocks randomly is selected to be the victim, next victim. In this case, we randomly pick D to be the next victim. So that's how this works. OK, and you can have the same questions I asked you before. You can look at the earlier lecture, right? I guess it's not here now. When does this policy perform better than LRU? When does this policy perform worse than LRU? And can you make this better? OK. Any questions? Let's look at LRU versus random. I told you several times that random actually can do better. And one of the main reasons is because you can have thrashing in the set. What does that mean? Basically, you have the set. Let's say it's 4-way associative. But you want your working set within the set is actually larger than 4 blocks. Maybe what you're doing is you're accessing A, B, C, D, E in a circular manner. And they all map to the set. And if you can only host A, B, C, D, you can only host 4 things. Well, what is the hit rate with LRU to that set if this is the case? 0, right? 0%. Because whenever you need to access the next block, the other blocks are in the cache because you're using least recently used policy. Right? So this is bad. And random replacement is actually better when this kind of thrashing occurs. If you do random replacement, you randomly pick 4 of those things. And the likelihood is that you will actually touch that next time. And you can compute that likelihood. That could be a nice exam question, actually. So I'll not solve it right now. Maybe Justin will be nice and he'll solve it in the recitation sessions. OK, I'm sure you guys have solved it in your head, in your heads. So in practice, this depends on the workload, which replacement policy performs, just because of this reason, right? Because some sets actually are very good with LRU. Some sets are very bad because it turns out your working set is much larger. This is also called the hot set problem. And we will see some other solutions to alleviate this at least. You have a lot of blocks that need to go into one set, and the associativity in that set cannot handle that many blocks. Whereas there are some other sets, you have too much associativity. Only 2 blocks access it. And why does this happen? Because we're indexing. We're using the address to index into the cache, right? Remember, we took these bits from the address as your index. And it so happens that some indices are more popular than other indices, right? Could be. Not everyone's. A lot of people search for the same thing on Google, right? I guess Lady Gaga used to be the most popular search on Google at one point in time. But there's a huge distribution over there. It's the same thing. And we will see ways of randomizing this. So instead of indexing just using these bits, maybe you want a randomizing function, predictable randomizing function to balance the utilization of your sets. But even that will not solve the problem. Even then, you may have thrashing just because you have too much data and your cache is too small. Right? So that's why random policy is desirable. In fact, there have been studies that show that average hit rate of LRU and random are similar across a large number of workloads. So this is very workload dependent. That's one of the other reasons why you don't necessarily want perfect LRU or true LRU to be implemented, because you don't know what your access pattern will be like. If you really know your access pattern, then you can design your cache to be optimized for that. But then you're becoming much more specific, application specific. OK, so you could actually have hybrid policies, which I will not go into, and choose between those hybrid policies. This is very similar to hybrid branch predictors, and people have proposed this for caches also. This is a paper we had written a long time ago now. The idea is dynamically detect which policy is performing better. Is it LRU? Is it random? And how do you do that? Well, sample the cache. For some sets, implement LRU. For some sets, implement random. Or emulate both policies in the same sets. Figure out what would have been the hit rate with LRU or with random, and pick one that would have done better. You could imagine how you build the hardware, right? It's relatively easy to build the hardware because now you're emulating what would you have replaced if you picked random, and what would you have replaced if you did LRU. Make sense? There are some implementation issues, but that's the idea. It's very much similar to a hybrid branch predictor. Say it again? Tournament cache. Exactly, tournament cache replacement. Actually, initially we called it tournament. It might be still called tournament. But that's the idea. And it turns out that does much better than LRU or random alone, because now you're dynamically adapting to the behavior of the workload. If your workload is actually thrashing the cache, you can figure that out very quickly, because it turns out the counters tell you that the counters that emulate the random replacement tell you that, oh, random would have done much better. Switch to random. Now, what is the downside? Now you have to actually implement the 2 policies as your replacement policies, right? So each of your cache sets need to be capable of doing LRU replacement and random replacement. So it's additional overhead, just like hybrid branch predictors. And you can imagine other replacement policies to be hybridized with these also. And we'll see some other replacement policies. OK, what about optimal replacement? This has bugged people a lot for a long time. And you may have heard of Beldy's optimal or opt policy. How many of you heard this? No? No Beldy's in 213? Not yet, at least. So this is a seminal paper that was published in IBM Systems Journal. Beldy actually studied the replacement algorithms for a virtual storage computer. This was for page replacement. And the idea is, well, in hindsight, it's simple, right? What is the optimal replacement policy if you want to minimize cache miss rate? Replace the block that's going to be referenced furthest into the future. Right? This assumes that this answer to this question, do you insert the incoming block into the cache, is always yes. Assuming that, this minimizes the miss rate to the cache. And you can think about it. Basically, you're going to replace things that, if you're not going to reference something ever, you're not going to, you're going to replace that. Right? So how do you implement this? Well, that's a tough one, right? You need to know the future. That's why it's optimal. Even simulating this is a little bit hard, and you may want to think about that. Simulating it online is a little bit hard while you're actually getting the stream, right? You need to do a 2-pass algorithm to simulate. OK. Is this optimal for minimizing miss rate? Yes? Some of you say yes, some of you are not sure yet. Yes?
Isn't the least recently used in that specific case the same thing?
Let's see. In this specific case, it's the same thing. If you have a circular, you're absolutely right. If you have a circular reference pattern, this is called a circular reference pattern. And if you have enough space in your cache, of course, you basically least recently used is the best policy. But this is a very particular access pattern, right? If you have other access patterns, then you need to optimal is very different from least recently used. But that's a good observation. Least recently used actually has been developed because people have seen these circular access patterns. Let's say you have an array. You scan through the array, do something, and then you go back and do something else with the array. And then you go back and do something else with the array. Right? So it's not a made-up pattern. It actually exists in programs. That's why least recently used has been very popular. So this is optimal for minimizing miss rate, and you can convince yourself or read this paper. I guess one question is this optimal for minimizing execution time? This could be a good exam question, too. Now you need to think, does minimizing miss rate always minimize execution time? And we talked about this in the last lecture. Remember that equation? Your performance is not only dependent on your miss rate, right? It's also dependent on your miss latency. And if you have accesses that are a lot more costly, for example, LRU may be optimal in minimizing your miss rate, but maybe keeping this in the cache is like refetching this block takes 10x times than refetching this block. Right? And you know that you're going to use it at some point. It's a lot more important than block C. And it may be better to keep this in the cache, even though it's going to be referenced later than C. Right? That's the idea. If your cache misses have different costs, you need to take that into account in your replacement policy if you want to minimize execution time. Yes?
Why would you get two separate blocks that take different amounts of time to access?
Oh, that's a good question.
Would that be because you might have to go through different layers of the hierarchy?
That's right. That could be one reason. Exactly, that's one reason. And we will cover some other reasons. One other reason could be you have a NUMA, non-uniform memory access system. OK, there should be one more here. Oh, these are all clean today. It could be that, let's say you have your processor 0 and processor 1. You may have a distributed system, right? You may have a multiprocessor. It's a shared memory multiprocessor. And we will cover some of this later on. It may be that the program you're running here, this is cache 0, this is cache 1. It's sharing some blocks between the different caches, and it's cached block A, which happens to reside in this memory. This is memory 0. And this is memory 1. And it also, well, I guess we had the C and D, right? C and D. And you bring in C and bring in D also. But D comes from a much farther place, right? It's not from this local memory. Maybe you need to go through a network or a small network to access this M1, right? And it may be that this is 10x latency compared to this, which is 1x latency. That's one other example. And we will see one more example, which is the overlapping of cache misses. Even within a single processor, even if you're getting C and D from here, or let's say C and E from here, it may be that when you fetch C, you only fetch C. Whereas when you fetch E, you fetch 10 other cache blocks. So you overlap the latency of fetch of E, which means that if you miss on E, there are other misses that are going to happen anyways, right? So if you eliminate the miss to E, you're not going to gain much because you overlapped its latency. Whereas if you eliminate the miss to C, it's an isolated miss. Once you eliminate it, you can reduce the execution time. So that miss overlapping, and you've seen that miss overlapping happens with out-of-order execution, that affects the cost of a cache miss. And we'll see this in a little bit more detail if we actually get to it. OK, so this is not optimal because this is not optimal for minimizing execution time because cache miss latency or cost varies from block to block. And I've given you one example of latency here, 10x versus 1x. And cost is, even though the latency may be the same, the overlapping determines the cost of the cache miss. A cache miss that happens by itself is a lot more costly to the processor. Well, I guess I've given you the 2 reasons here also on the slides. OK. And this is the paper that also covers this. And I'll briefly describe this later on, I think. So just as an aside, you've actually seen replacement policies a little bit when we covered virtual memory, right? Because page replacement is essentially similar to cache replacement. Because physical memory is a cache for a disk. DRAM is really a cache for a disk. It's a software-managed cache. It's managed by the system software. That paging, demand paging, is really managed by system software. Which means that page replacement is similar to cache replacement. And page table, you can think of the page table as a tag store for the physical memory data store, right? Your physical memory is your data store, and your block size is the page size, and your page table is essentially a tag store. It's managed in software. Does that make sense? Which means that you need to have replacement algorithms for pages anyway, because your physical memory is not infinite. And you could have perfect LRU in your page replacement as well. In fact, LRU algorithm was developed for page replacement initially. Now, of course, you don't do page replacement using LRU, right, in modern operating systems. Do you guys know how some of the operating systems operate? Like what kind of replacement policies are used? Yes? No? You haven't learned this? OK, we can cover one policy. But what is the difference between these two? Let's take a look at that. What is the difference between caches, hardware caches, versus physical memory? Yes.
Pages are large, very large.
That's right. Pages are very large. That's one difference. And there are many of them, right? The other difference is hardware versus software management. Software manages the physical memory. So whenever you get a page fault, you need to bring in some other page. And software gets involved in that. Actually, you could do that in hardware too, but that gets complicated. Number of blocks in a cache versus physical memory, that's a big difference, right? In physical memory, you have 4 GB physical memory, let's say, and you have 4 KB pages. How many pages do you have? Lots. So if you want to design a replacement, and usually physical memory is not designed as associative, right? Page table, if you look at it, any virtual page can map to any physical frame. You can think of it as a fully associative cache to disk. So how do you do the page replacement? Well, you probably don't want to have an ordering, LRU ordering of 4 GB divided by 4 KB blocks. I guess what is 4 GB divided by 4 KB? That's 2 to the 20, right? 1 million, I think. Yeah, 1 million blocks. And also, you need to basically, these differ in the tolerable amount of time to find a replacement candidate. So if you look at physical memory, this is your physical memory. Let's say you have 1 million pages. You want to find a replacement candidate relatively quickly. You don't want to search for this, right? Think about how a fully associative cache where associativity is 1 million. What is the ordering? How many different orderings are possible? It's 1 million factorial, right? That's a big number. So you don't want to do LRU. That's one of the reasons people have developed approximations to LRU in operating systems too. But the idea is, how do you, one way of doing page replacement, one popular algorithm is the clock algorithm. And the idea is, in the page table, for each entry in the physical memory, for each page, you keep a bit. This is the page table entries. And this bit says, this bit is the accessed bit, or recently accessed bit, 1 bit. Initially, all bits are 0. Whenever you, now when you bring in, let's assume that you brought in a page into physical memory, you set the bit. Basically, you touch the page. You access the page. And let's say you access another page later on. You set that bit for that page. And then you access another page. You set that bit. Now, how do you do the replacement? Let's assume that you need to bring in another page, and you would like to replace some other page. This is your physical memory, and it's full in the page table. You're bringing page A, and you would like to replace a page. The idea is you don't want to replace a page that's been recently accessed. You don't want to replace a page whose access bit is set. So in the clock algorithm, what you do is you have a pointer, a single pointer in your physical memory that says, this is the replacement candidate. When the operating system needs to replace a page, it basically checks that replacement candidate's page table entry, checks the access bit. If the access bit is 0, that's the one that's to be replaced. So replacement is very quick. Right? Now what happens if the access bit is 1? Well, that means that this replacement candidate was recently accessed. Right? Because you set the access bit to 1 whenever you get an access to that page. In that case, the operating system says, oh, I'm not going to replace it. Let me look at the next thing, next physical page or physical frame. And the system software goes to the next page table entry for the next physical page and checks the access bit. If it's 0, that's great. That's replaced. Right? And then it moves the replacement candidate pointer to the next one. Does that make sense? So you basically have a replacement candidate pointer, and you check if you can replace that candidate. If not, you increment the pointer. You check if you can replace the next candidate. And you will do this until you find a replacement candidate that has the access bit 0. Right. That's the idea. That's the idea of the clock algorithm. And people have developed many, many modifications to clock. So what is the advantage? Now you don't replace things that have been recently accessed. And you can find your replacement candidate relatively quickly. Now what happens if all of your access bits are 1? Well, it'll take a while to figure out what to replace, right? So what the system software usually does is it gives up after a while. If it sees all of the bits, all of the pages have their access bits as 1, then it has a threshold. After so many times, if I cannot find an access page, I'm just going to replace the page at the replacement candidate. It's a heuristic, right? So, OK, that's one question. Another question is, what happens, when do you reset these access bits? Right? This is 1 bit, right? Hopefully you reset it sometimes. And the idea is periodically the system software goes and resets these bits. You can imagine the overhead associated with that. People have tried to optimize that overhead. So periodically you say, you go and reset these bits. Yes?
I believe x86 systems have power support on resetting those bits.
For resetting?
For resetting.
That's right, yes. Mm-hmm. So I didn't go into details, of course. Some of these operations are happening on the TLB also, right? Because TLB, whenever you access, TLB caches the page table entries, and access bits are actually updated in the TLB. Okay? So you could actually decide to replace. So one other heuristic could be replace a page in your DRAM that's currently not resident in your TLB. Right? Because TLB essentially houses those translations that have been recently used. So by definition, most recently used pages, their page table entries are actually cached in your TLB. So one heuristic could be replace a page that's not present in your TLB. Okay? So that's the idea. So if you look at this accessed bit is very similar to the replacement policy bits that we've seen, except this is very, very simple, right? You could think about implementing such a policy for caches also, for a fully associated cache. And I'd encourage you to think about that. But page replacement is essentially very similar to cache replacement, except with these three differences. You can do this in software, which means that you can probably examine more entries, but you have so many blocks in physical memory that you need to have an efficient mechanism still. And maybe you can tolerate the amount of time to find a replacement candidate here, right? Because you're going to bring the page from the disk anyway. So you have some time to actually decide this. It takes a long time to bring the entire 4 kilobytes from the disk. The latency is high. So this replacement, maybe you can actually search a lot of entries here, right? While you're waiting for the disk page to come back from the disk. Whereas in cache replacement, it's not the case. In cache replacement, you're going to get the block maybe 20 cycles later from the next level. Right? So you'd better figure it out quickly. OK. I think we've covered this, right? Actually, if you look at this access bit, this is similar to replacement policy bits, right? And if you look at this, this is the page table, or page table entries here. Page table entries are the tag store for your physical memory. So we have the replacement policy bits in the page table also. In a cache, what's in a tag store entry? We briefly covered this, but I just want to make sure that this is clear. Where is this? Anybody see? Oh, it's up on the. OK, thanks. Look, there's the optimal policy here, too. Somebody predicted what we were going to cover. So in a tag store, this is the tag store entry, this is the data store entry. You need to have a val bit saying that your block is valid or not. Obviously, you need to have the tag, and it's useful only if your block is valid. And you need to have some bits for replacement policy. And this may be per data store entry, or per way, or it may encompass all of the ways, right? For example, in a direct map cache, you have 1 bit for both ways. Whereas in a next victim policy, you may have 2 bits per way, right? And you also need something else, maybe, which is a dirty bit, right? You guys know about the dirty bit? Is the cache block modified? Again, this is very similar to page replacement, right? If you remember virtual memory, when you write to a page, you have another bit here saying modified. I guess I'll add that bit, modified. This is how the operating system keeps track of the modified pages. Because if a page is not modified, you don't want to write it back to the disk when it's getting replaced. Right? Whereas if a page is modified when it's getting replaced, you'd better write it back to the disk so that you don't lose the updates to that page. Same as in caching. Has this block been modified or not? Right? It's the same bit. Of course, you may or may not want to have this in either case. You have the dirty bit if your cache is write back, right? If it's a write back cache. You don't need the dirty bit if your cache is write through. Now, what is the difference? Well, now let's take a look at how writes are handled in the cache. This is what I promised in the previous lecture. When do we write the modified data in a cache to the next level? And next level could be memory or the next level of caching. Write-through policy says at the time the write happens. Basically, when you write the data, if you're writing a piece of data into your block, don't only write it to this cache, but also write it to the next level. That's write-through. The write goes through the cache. And write-back means, well, write the data now, but don't notify the higher levels, the next level. That's write-back. When the block is evicted, that's when you do the write-back. That's the idea. You write the entire block back to the next level. So what are the trade-offs associated with this? Why do we want write back? Or do we want write back? No? Yes?
Well, it means that every time you do a store, you don't necessarily have to access a higher level.
That's right, exactly. Well, I guess this is a different one, but there you go. But you can potentially save bandwidth between cache levels, which translates into energy savings also. Basically, you can consolidate multiple writes to the same block before eviction also. So you save bandwidth between levels. So if you have another level here, you don't keep writing back. Especially if you're writing a block quite a few times, you can consolidate those writes in that cache. Of course, the downside is now you need a bit in the tag store indicating that the block is modified, right? Well, you have additional complexity also. If you do write-through, well, there must be an advantage to the write-through, which is simpler. And all levels are up to date. This is one other advantage. Now you don't need to you don't have a coherence problem, right? Coherence problem exists across the levels also, right? So you may have a block A, that stores the value 1,000 here, and it's modified, it's dirty. And you may have the same block A here, but it happens to store the value 0, because you didn't update the next level, right? Now what if some other processor requests this block? We haven't covered the multiprocessors yet, but it's good to think about it right now, because these decisions will affect what happens in multiprocessors. Let's say another processor requests A. That request goes through the bus to this processor, and the question is, what is the value of A? If this highest level is up to date, then you don't need to check the lower levels, right? If this highest level actually says, oh, I have A, and here's its value, and I know that it's up to date, then you get the value. But if these levels are not consistent, you need to check the different levels. Right? So that makes this consistency harder, because you have different versions of the block inconsistent across your different levels. Yes?
In a write-through case, would all the levels of the caches definitely have that block in them?
No. So that's another. That's not necessarily true, right?
So what happens if the lowest level of cache has that and have it into it, but the next level does not have it? So how does it write through?
So that way you write through to memory, right? You can define which levels do you actually have write through. Does that make sense? So what you're saying is another dimension of caching. Let's see if we have. I guess I don't have it here. We'll cover it later on. But are your caches inclusive or exclusive? Right. Inclusive means the higher levels of cache always contain the blocks that are at the lower levels. So if A is here, A must be at the higher levels also. That's inclusive caching. Exclusive means exactly the opposite. If A is here, A cannot be here. They have exclusive contents. Now there's one other option, which is non-inclusive. You have no guarantees, basically. If A is here, A could be here also, but it's not guaranteed to be there, nor does it not have to be there. And these have effect on coherence that we will see later on. But if you do write through, then this also determines where your blocks are. Okay, so write through is simpler, and it enables easier consistency. The downside is, as we've discussed, it's more bandwidth intensive, right? You always need to write through. And there's no coalescing of writes. In many cases, when you write to a cache block, you write to many different locations within that cache block. You can think of when you're updating an array, right? If you do this, ci equals ai plus bi, you bring in a chunk of the ci that's of the size cache block, and you keep writing. If all of these writes are exposed to the next level, then that's a lot of bandwidth. Whereas you can just coalesce those writes in a single cache block. Okay, there's another decision to make in terms of writes. Do we allocate a cache block on a write miss? So you're doing a write miss. What is a write miss? It's a store miss. The processor is doing a store, and it's got a cache miss. Do you actually bring the cache block from memory and then do the store, which requires you to wait, the processor to wait for the transfer of that entire cache block, even though you may be doing a store for 4 bytes. Right? Or do you actually not allocate the block? Well, what are the trade-offs? If you allocate it on a write miss, now you can consolidate writes to this block, right? Instead of writing each of them individually to the next level. If you don't allocate the block, then you need to write 4 bytes all the way to the next level and all the way to memory, potentially. Does that make sense? So for example, if you had actually brought this block all the way into the cache and you've allocated it, then you would just do writes 4 byte by 4 byte to that block. And again, if you do allocate, this is simpler because now your write misses due to stores can be treated the same way as read misses. Right? You don't need to have a special case in your design. The downside is, well, it requires the transfer of the whole cache block. Right? What if you're just doing a byte write? You need to transfer your entire 256-byte cache block if your cache block is that large. So there's a trade-off. If you don't allocate on a write miss, this conserves cache space if locality of writes is low. Right? For example, you do a write to one block, and you don't allocate. You just do the write through the cache, meaning you don't have a block allocated for that write, but the write goes to the next level directly. If that's the case, you save cache space, right? Because you don't pull in a block into the cache. And this is useful assuming you're not going to use that block. Make sense? OK. So these are actually policies. There's no best policy, by the way, in this case. It's a trade-off again. Well, the downsides of no allocate did not fit in this slide, but you can actually reverse this part. And that'll be the downsides of no allocate. OK. So I have a question mark here. This requires the transfer of a whole cache block. People have realized that this is a problem. Writes are a problem in caches. And they've developed something called sectored caches. And the idea here is you divide a block into a subblock or sector. This is called a sector or subblock. This is a subblock cache. And have separate valid and dirty bits for each sector. They share the same tag. The subblocks share the same tag, but they have separate valid and dirty bits. When is this useful? Now let's assume your subblock is 4 bytes and you're doing a 4-byte store. You don't need to transfer the entire cache block from memory, right? What you can do is you can make that subblock that you're writing to, let's say you're writing subblock 0, make it valid, make it dirty, and store the tag over here, and have another valid bit for the entire block. Now you have a cache block in the cache that you've written to, but you've written to only one subblock. All of the other subblocks are not valid. This way you can do a write without bringing the data, the entire block, from the main memory or the next level. That's the benefit of sectoring. And in fact, this is even more beneficial if you're doing something like this. If you're actually doing a streaming write, you can imagine that this is a streaming write. Streaming means you keep accessing the consecutive locations and you keep writing to the consecutive locations. Now if you're doing this, let's say C0 is written here. In the next iteration, you write C1. You validate and dirty that subblock. In the next iteration, you write C2. Next iteration, you write C3. So that streaming write now validates the entire block, and you've never brought the block from memory to the cache. So you've saved bandwidth by doing this. Basically, no need to transfer the entire block into the cache. A write simply validates and updates a subblock. Now you have also more freedom in transferring subblocks into the cache. Right? A cache block doesn't need to be in the cache fully. You can have partial blocks into the cache. So you can have more sophisticated policies now. You can say, maybe when I access this block, I only access this subblock. So I'm going to bring only that from memory. And you can store only that because you have individual valid and dirty bits for that subblock. Does this make sense? You guys can devise policies even perhaps. That could be, you could do that part as part of your lab 5 assignment, since you're optimizing the caches. You could actually implement a sectored cache and see the benefits as your cache optimization. Yes?
Isn't this really just having more smaller cache lines with a simpler direct mapping algorithm?
You're stealing my exam questions. But that's a great question. What's the difference? What's the difference from between this and a smaller cache line or cache block? Less overhead. Why is it less overhead?
Like you only shares one path for all of them.
Exactly. Yeah, that's the difference, right? Here, your tag. If you have smaller cache blocks, if you think of this as a cache block, you need to have a tag with each of them, right? Whereas here, you have one tag associated with many subblocks, which means that you're actually storing that block in there, except you're storing partially, potentially. So if you have smaller cache lines, you have more overhead because your tag should be larger. Right? It's not as flexible. This is not as flexible as smaller cache lines. Here you can have much bigger blocks while getting some of the benefit of smaller cache lines. And the main reason, again, why this was invented is you want to get the benefit of smaller cache blocks, or actually you don't even want to bring in any cache block into the cache if you have writes. Okay? Okay, of course, downside is more complex design, right? And complexity comes from these valid and dirty bits within each subblock. Well, that's a great question. What are the trade-offs between smaller cache blocks and a sectored cache? Okay, I guess it's also true that it may not exploit spatial locality fully when used for reads. Oh, my computer is updating itself, huh? Oh, we have a critical office update. Do you think we should do it, or should we risk not having the rest of the lecture? I guess it wasn't that critical. Okay. Okay, let's talk about instruction versus data caches also, and then we'll take a break. Traditionally, these have been treated separately, but you could have unified instruction and data caches also, right? If you have unified instruction and data caches, you can dynamically share the space between instructions and data. And the idea is here, if you have a single space for caching memory, and you don't divide it between instructions and data, which enables you to have better efficiency in caching, right? Whenever you have dynamic sharing of space, there's no over-provisioning that might happen with static partitioning. This is, again, static versus dynamic partitioning. And we've seen this in reservation stations, if you remember. Do you have distributed reservation stations separate for each functional unit, or do you have a single monolithic reservation station? Again, the idea is similar. Do you have caches for a separate cache for instructions and data, or do you unify them? And the trade-offs are actually a little bit similar also. And we'll see this later on in multi-core. Let me actually show that over here too. If you have multiple cores, let's say 4 cores, do you have a shared L2 cache here, or do you have private L2 caches? Or private caches at some level. Do you statically partition the space, or do you dynamically partition the space? And the trade-offs are similar. Here, if you have separate caches, if it turns out that your data set doesn't fit into your cache, it's larger, data working set is larger than your cache, and instruction working set is smaller, well, too bad. Right? You cannot use this space for data. Right? Whereas if you have a unified cache, maybe what happens is this is your, I guess, data, and these are your instructions, and they can nicely fit in your cache. Right? Dynamic partitioning. Downsides? Well, it may not always work this way, right? It may happen that your instructions are actually barely fitting into your instruction cache, and your data is huge. Now, if you actually have a unified cache in this case, your instructions are occupying this much, and your data is getting rid of your instructions from your cache, depending on your replacement policy. And if your data set is huge, then you may be missing your instruction cache all the time. Right? So that's one reason to separate these caches, because if you think about it, instructions are very important. If you don't fetch an instruction, you will not be able to fetch the data for that instruction. Right? You'd like to fetch that instruction. Otherwise, you cannot feed the pipeline. And that's one of the reasons instruction cache is separate. There's another reason. I and D are accessed, instruction and data caches are accessed in different places in the pipeline. Right? And we talked about this before. If you look at the pipeline, this is especially true if you have a long pipeline, you want to do the instruction fetch here, and you want to do the data fetch farther. And usually these are not easy to put together in a pipeline, easy to lay out together. So what you do is, it's easier to partition instruction and data caches to minimize the latency. If they're unified, then you need to have a network or some connections from both parts of the pipeline to access that unified cache. Whereas if they're separate, the access latency here is faster, and you don't need to deal with the connections across the pipeline. So you have an instruction cache that feeds the beginning of the pipeline, and data cache that feeds the data stage of the pipeline, memory access stage. Okay, and first level caches are almost always split today. And for that reason. This is the main reason. Because again, remember, first level caches, the design decisions you make there are dictated by the pipeline. You'd like to supply instructions and data right away into the pipeline, in one cycle ideally. And if you have a unified cache, going through from the instruction stage to the unified cache takes time, or going from the data fetch stage to the unified cache takes time. Whereas you get rid of that if you separate the caches. Right? And second and higher level caches are almost always unified between data and instructions, although it's not always true. There are some processors that do split instructions and data at the second level too. For the reason that I mentioned earlier, which is gone now, you want to protect your instruction cache space. Because instructions are a lot more critical for your performance. Right? If you cannot fetch them, and if you have a big data set, and if you have a unified cache between instructions and data, your instructions may be thrashed. And there are workloads like that. You have a large instruction set, like online transaction processing workloads usually have large instruction sets and much larger data sets. So you want to protect your instructions. So there have been processors that are designed where second level caches are separate between instructions and data. Okay. I guess I'll cover this too, and then we'll take a break. First level caches, decisions are very much affected by cycle time. They're smaller, lower associativity, and usually tag store and data store are accessed in parallel, right? Because you want to get the data quickly. Second level cache decisions need to balance hit rate and access latency. Now, access latency is not the only thing, right? Your hit rate is very important too. As a result, they're usually large and highly associative. Latency is not as important, but it's still important. That's why we keep adding more levels into the cache, right? And you can have the tag store and data store accessed serially now. Right? So what you can do is, so what benefit does this give you? Oh. I guess which one should we? This is another design decision that you need to make in your caching, right? Do you actually access the tag store and the data store at the same time? What is the upside of accessing them at the same time? You don't need to wait for a tag match to get the data. Right? What is the downside of accessing them in parallel? Well, what if you don't have a tag match? Then you've accessed your data store for no reason. Right? You wasted power. In fact, that data store access can be very power inefficient, right? If you have, let's say, a 32-way cache. What you're doing is powering up 32 different ways and getting data out of them in parallel, and then you're maxing out data to figure out if there's a tag match. Well, to figure out which data that you bring in. And all of this may be useless because you may not even hit in the cache. Right? So data store access, doing the data store access in parallel with the tag store access is actually speculative. Right? You don't know if you need this data. This is speculative access. So you could do this serially. If you do this serially, basically you first check if the tag matches and if the block exists in the cache. If the block exists, now you know actually which way the block exists in, right? So you can power up only that way if you do serial access of the tag store and the data store. Instead of powering up 32 ways, you power up only one way if the block exists in the cache. And if the block doesn't exist, then you don't even need to access the data store. That's the advantage of serial access of the tag store and the data store. Make sense? And this is done usually in second-level caches and beyond, third-level caches. Most processors today have this serial tag store and data store access because access latency is not as critical there, and power is very critical. In fact, even in first-level caches, to have high associativity, some processors try to not power up all the ways. You want to have high associativity, but powering up all the ways. Let's say you have an 8-way first-level cache. This was what Pentium 4 had, actually. You have an 8-way first-level cache, and let's say 50% of your instructions are loads and stores. If you do that, you really need to do the search, powering up of your data store 8 of the ways, even if you're not going to hit. What some of these processors did was they employed sophisticated techniques. One way was to predict whether or not they're going to hit or miss in the cache. That way you can reduce the accesses that you do in the data store. The other idea was to use the way prediction. And you can see how sophisticated this can get. The idea is don't power up all the ways, but predict which way you're going to get the data from based on what happened in the past. And Pentium 4 employed this. Yes?
Doesn't that need to access a prediction buffer?
That's right, yes. But that prediction buffer can be smaller and maybe made much more power efficient. Because if you think about this, let's say these are 64-byte lines, right? If you have an 8-way cache and 64-byte lines, you're accessing 8 64-byte lines and driving them down, right, in the data store. And that's very power inefficient. If you have a way predictor that says, or a hit-miss predictor complemented with a way predictor, now you can decide intelligently whether or not you should access the data store. That's what the hit-miss predictor says, basically by looking at the program counter, for example. And the way predictor may also look at some bits of the address of the load and say, oh, that's going to be in this way. So power up only this way. These two predictors together can be much more power efficient than bringing down all the data from 8 ways. And also accessing, also powering up the word lines in the 8 ways, right? So that's the idea. So a lot of the caches that you see today in processors are very, very optimized. And it's kind of similar to branch predictors, right? I'll not get into why this works, but you might want to think about why this works. It's not perhaps as intuitive as branch prediction. Because ways are determined based on conflicts, right? Why does this work? Yes?
So they can get prediction good enough that the misses aren't as, it's not too expensive to miss?
That's a good question, yes. I don't believe that the data is published, but usually there is good prediction accuracy. It's harder with the data caches. It's easier with the instruction caches. Because instructions are more predictable, right, in terms of where you go. And way predictors, one of the papers that I recommended to you, the Alpha 21264 microprocessor, had a line predictor, like which line you're going to access next. So they had a way prediction mechanism too. But the trade-off they made is, yes, the accuracy is high enough that it's better to do this than power up the entire cache. OK, there's one more trade-off, and then I'll take a break. Serial versus parallel access of levels, right? This was serial versus parallel access within a level. Do you do serial tag store or data store access? Do you do serial access of the level 1 cache and level 2 cache? Or do you do parallel access? That's another trade-off. Many processors do the serial access. Second level cache is accessed only if the first level misses. Again, the assumption is that you're going to hit in the first level, right? And that's true usually for L1 caches. You get around 90% hit rate or higher on average across many workloads because programs have locality. Parallel access, well, in this case, second level does not see the same access as the first. First level acts as a filter, right? Parallel access means that you speculatively access the second level. The upside of this, if the first level doesn't hit, you get the data earlier from the second level, right? You reduce your latency. If you predict that your first level is going to miss, you may want to do that parallel access, initiate that access early. OK, I think let's take a break here, and then we'll cover virtual memory and cache interaction, which I'm sure all of you have been looking forward to. We've looked at the similarities between virtual memory and caches in terms of replacement, right? Essentially, DRAM is a cache for disk. And we've looked at how you do replacement in virtual memory and caches. Let's take a look at how they interact. There's another point they're similar. Actually, they have to interact somehow, right? So far, we've assumed that you get a load address, and you access the cache. Is that address a virtual address or a physical address?
It depends.
It depends. What does it depend on?
Your design decisions.
That's right, exactly. It depends is a good answer, usually. But yes, and the answer is it does depend, actually. And hopefully it will depend if I can make my computer work. So when the key design decision is when do you do the address translation? And do you do it before or after accessing the L1 cache? It looks like this decided not to work today, or after. Oh, there's a good reason why it doesn't work. OK. That's a user error. That's the cause of most reliability issues in computing. User error. OK. When do we do the address translation? Before or after accessing the L1 cache? And this decision actually leads to a lot of trade-offs, a lot of issues that you need to handle. You could use a virtual address to access the cache, or you could use a physical address, or you could use a hybrid somehow. And you can have a virtual cache versus physical cache. Let's take a look at a virtually addressed cache first. What are the issues with it? Is there any issue? You take the virtual address, and you do the indexing as we described. Virtual address, and you have a byte and block, and you have an index into the cache, and that's how you go into your cache. Yes?
Most virtual addresses are the same,
Most virtual addresses are the same.
at least between different programs.
OK, yeah, that's one issue, right? It may be that you have two different programs. They have the same virtual address, but they have different physical addresses, right? Because they're totally different programs. Well, you don't want to go into the cache with one program's virtual address and get another program's data, right? So that's one problem, and this is called the homonym problem. Homonym problem. Two virtual addresses mapped to the same physical address. Oh, the other way around. It's the same virtual address mapped to two different physical addresses. And you need to handle that. But there's also the synonym problem, which is what I said earlier. Two virtual addresses mapped to the same physical address. And this happens when different programs share data, right? Which means that if you have the same physical address can be present in multiple locations in the cache, right? Which can lead to inconsistency in data. Right? So if you, I guess, let's take a look at a virtual cache. If you have a virtual cache, and if you have homonyms, now the virtual address is mapped to one the virtual address for this program is mapped to physical address x, and you want that x to be there in the cache. Now, if you're accessing the same virtual address from a different program, you don't want x to be there. You want something else to be there. So how do you handle this? Well, you can handle this with tagging somehow the cache lines with what is called an address space ID, right? Program ID. Let's not get into that, but this is an easier problem to handle. The harder problem is the synonym problem. If you have two virtual addresses mapping to the same physical address, if your cache is virtual, now those physical addresses are at different locations, right? Does that make sense? Because you have virtual address 5, let's say, mapping to physical address, I don't know, I guess 5 is not a good thing. 5,000 mapping to physical address 15,000. And you have virtual address 50,000 also mapping to physical address 15,000. And if your cache is totally virtual, these two virtual addresses will be in different locations in the cache. Whereas they have the same data, really, because it's really the same physical address. Right? Which means that when you update it with one virtual address, you'd better update the other one also. So you have a coherence problem. Make sense? Let's take a look at how we can actually solve the problem. This can lead to inconsistency in data. OK, so homonym, same virtual address, can map to two different physical addresses. And you've seen why, what the reason for this is. And you can imagine solutions to this. This is an easier problem to solve because you can tag the cache lines with address space ID. But some of the solutions that we'll describe will solve that problem also. Synonym, different virtual addresses can map to the same physical address. Why? Because different pages can share the same physical frame within or across processes. We can have shared libraries, shared data, copy on write pages within the same process. Those are the many reasons. Well, I think the answer is yes. I already answered this question for you. Homonyms and synonyms create problems when we have a cache, especially when you have to do this when you have a virtual cache. So you have design decisions, basically. One solution to the problem is this, right? You don't access the cache until you do the address translation. That solves your problems, right? You do the address translation. After that, you access the cache. This way, both problems go away. Now, the downside of this is you really would like to access this cache very quickly, right? You don't want to go through this address translation because it takes time. So this is not a good option. We're going to eliminate this. This is not a good option for the first level cache. Because, again, remember, the first level cache, you want to access it very quickly. Another option is having it totally virtual, and we solve problems with that, right? Basically, you do the translation after the first level access, and this usually doesn't make sense. Well, this may make sense for critical path reasons. We will see. But there are other solutions. There are other problems that are caused by it, these two problems that limit the effectiveness of this. So many processors today use something like this. It's a virtual-physical cache, or virtually indexed physically tagged cache, as we will see. You do the translation in parallel with the cache access. This way, you overlap the latency of the cache access with the translation, but you somehow need to index the cache with the virtual address, right? Because you cannot start the cache access if you don't have well, you can only start the cache access in parallel with the virtual address because you don't have the physical address available yet. Let's take a look at, well, we'll take a look at that design. So physical index, physically tagged, it's very simple, right? You basically use you go through the TLB. TLB translate the virtual page number to a physical frame number, and you use that entire physical address to index into your cache, which means that a physical address can be in only one location in the cache. So this eliminates the problems. Virtually indexed, virtually tagged cache, this is completely virtual cache. Now, if you look at this, you can view your address in two different ways. This is your virtual address, and you have a page offset, right? And a virtual page number. And if you're using the same virtual address as part of, to access your cache, you do the translation much later. You have a byte in block and an index into your cache and a tag for your cache. Right? You're using the same virtual address. Now the problem is a virtual page can be in many different indices in the cache, right? In many different locations. If you look at this, yeah, your index is virtual and your tag is virtual, right? Which means that you have the synonym and homonym problems. So virtually indexed physically tagged cache, the idea is to try to eliminate these two problems, or the synonym problem. The idea is this. While instead of accessing your cache fully with your virtual address, Let me draw this here again. I guess in the meantime, you can look at the picture too. This is your virtual address. You have your page offset and virtual page number. You go through the TLB to translate it to a physical frame number. And page offset goes unmodified, as you remember. In the meantime, you treat the same address as a different way. You basically take some bits from this address as your index and index into the cache. This is a virtual index now, right? And this index goes to the data store and the tag store. Well, I guess tag store and the data store. And you have a tag that's stored here. And this tag is physical. It's based on the physical address. I'll call this the physical tag. In other words, this is the physical frame number. Right. Now, if you do this, you get the physical frame number after the TLB access, and you simply compare that to the tag. If they match, you got a hit. Right. This way, now what happened? Your physical address, you got rid of, your virtual address could have been anywhere in the cache. You got rid of that a little bit because your tag is now physical. Now, if you choose your index such that your index actually does not cross the boundary here. So if you look at this, there are some bits that change during translation. These bits change during translation. Virtual page number is translated to physical frame number, and they change during translation. If you choose your index from your page offset, they don't change during translation, right? They're the same as your physical address, which means that if you index your cache with this part of your virtual address, then you don't have the synonym problem. A physical address can be only in one location, right? Does that make sense? And you compare the physical tag, that means you've eliminated the changing portion. Your physical address, a physical page, a physical block can be in only one location. Now the problem is if your index actually crosses this boundary, if you use some of the bits from the virtual page number to index into your cache, now what happens? Let's say you use 1 bit from here. And if you have 2 virtual addresses mapping to the same physical address, and they happen to differ only in that bit, and this bit changes during translation, now you get 2 locations where the same physical address can be, right? That's a location with 0 index and the location with, well, index, I guess index will be, 0 dot dot dot, whatever bits you get here, and 1 dot dot dot. So now you can have the same physical block in 2 different locations of the cache, just because your virtual address changes during the translation, right? So you can have the same physical address. Let's take a concrete example. Let's say you have, let's say this is 3 bits. You have virtual page number 000 and virtual page number 001 mapped to physical frame number 01. If this is the case, this physical block that is at 01 can be present in 2 different indices, 0 and 1. So we still haven't solved the problem. OK. So how do you solve the problem? What I said here is if your cache size is actually less than page size times associativity, and you can figure this out, the cache index bits come from the page offset. So one way of solving the problem is ensuring that a physical address remains in only one location is you always index your cache with the bits that do not change during translation. That way you ensure that your physical address, the index of the block, or for a given block stays the same with virtual and physical addresses. The problem is now your cache size is limited. Right? You can only have so many index bits coming from your page offset, right? If your page size is 12 bits, and if your cache block size is 6 bits, now your index bits could be 6, and you can only have 64 blocks in your cache, right? Well, it's not exactly true because you can now increase your associativity, right? Because this only determines index, where you index in the cache. You can have as many ways as you want in that index. So if you have this solution, if you just keep your index coming from the page offset, the maximum cache size you can have is page size times associativity. Why? Because your index can come maximum from here, and the rest is your byte and block anyway. So you have the page size, and you can have as many associativity as possible for that page size. Right? I'll let you convince yourself that that's true. But that's the idea here. You check the physical frame number. But there are still problems. You do want a cache that's larger than this. That's larger than page size times associativity. Then the question is, how do you achieve that? Is this clear for everyone? Basically, you have two virtual addresses mapping to the same physical address, and that physical address is in two different locations. And the different locations differ in one of the index bits in this case. It could be more of the index bits, right? If you actually take more bits from the physical virtual page number. So how do you solve this problem? There's a problem in that case. Well, one solution we said is limit cache size to page size times associativity. Get index bits from the offset only, such that they don't change, such that the physical address remains in only one possible location. But this limits your cache size. Another solution is basically implement coherence, right? And that's that was how it was done in Alpha 21264 and MIPS R10000. The idea is, the problem happens if you have two, let's say you have the physical frame, a physical block, and we call this block 0, 1, right? Physical block 0, 1 here and 0, 1 here. And one is at index 0, dot, 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 dot is here. And the other one's at 1, dot, 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 and dot, dot, dots are the same because they didn't change. When you write to one virtual address, when you write to this address, you also check if that physical address also exists in the other index where it could possibly exist. Right. So when you write to address 0, 0, 0, you check there's a physical address 0, 1 here. Does that also exist at address 0, 0, 1 or index 1 in the cache? Right. If it does, then you invalidate this, or you do the write into both locations. That's the idea. So you implement coherence. The other idea is you can restrict the page placement in the operating system. Right. So when you actually do this translation, you can tell the operating system that somehow you're using these bits from the virtual page number as part of your cache index. Operating system, keep these bits the same in the physical frame number. So never allocate, ensure that the index bits coming from the virtual page number do not change during translation. Does that make sense? This is called page coloring. And this is used in many Spark processors. They've designed their processors and the operating systems together so you can do this, right? That's the idea. That way you can actually design a very large cache and not have this problem, right? Because the operating system never changes these bits. So now what's the downside of this solution? Now it reduces the flexibility of the allocation in the operating system, right? Because the operating system, if your virtual page number ends with a 0, the operating system cannot allocate a physical frame number that ends with a 1 for that virtual page. And if the number of bits you take from the virtual page number as your index increases, your flexibility decreases. Okay? So I was going to go through an exercise, but in the interest of leaving you early, maybe I'll let you do this exercise. This will reinforce the problem that I've described here. This is a problem from one of the earlier exams a few years ago. And it basically asks you, let's see. Well, I'll let you go through it, I guess. It basically shows you two processes sharing this toy computer. And these processes share some portion of the physical memory. And it gives you some virtual page to physical frame mappings of each process. So if you look at process 0, you have page 03715, virtual, mapped to physical frame 0713. And process 1 has this, virtual page 01711, mapped to physical frames to 4532. And the question is, give a complete physical address whose data can exist in two different locations in the cache. And the cache is virtually indexed physically tagged here. And what do you look at here? If this is the case, if you have a virtually indexed physically tagged cache, you'll look at what frame, physical frame, actually is shared between the different processes. Right? So frame 3, if you look at frame 3, it's actually present in the mapping table of both processes. Here, page 15 is mapped to frame 3, and here, page 7 is mapped to frame 3. So you'd better start with frame 3. Right? And frame 3 is your physical address, which means that any byte in frame 3 can exist in different locations in the cache. Right? And what is frame 3? Basically, you have your physical frame number, and you need a page offset. And in the earlier parts of the question, well, your physical frame number needs to be 1, 1. And I believe in this question it's 6 bits. So you have 0, 0, 0, 0, 1, 1. And any 2 bytes here, and I don't remember how many bits this was. I believe it was 3. Oh, yeah, it is 3, right? If you look at the question here, it says the page size specified as 8 bytes. So you have 3 bits specifying the page offset. So these two, give a complete physical address whose data can exist in 2 different locations. That's the physical address, right? Your frame number concatenated with the page offset. And then you can give the indices of those 2 different locations, but I'll let you figure that out. Okay? Or do you want me to go through it right now? I think I'll leave you early today. But solve this problem. This will give you a good understanding of virtual to physical mapping issues related to caching. Okay, have a good weekend.